Hydrogen is usually something we manufacture. We produce green hydrogen using renewable electricity. We produce blue hydrogen from natural gas with carbon capture. But there is another possibility that is now attracting global attention. What if the Earth is already producing hydrogen naturally, deep underground? This video explores natural hydrogen, how it forms, where it may accumulate, how it can be produced, and why it could become an important clean energy resource for the future. Today, we will discuss not only the science, but also the development strategy, global research landscape, and the key challenges that must be solved before natural hydrogen can become a real energy industry. Here is the roadmap for today's video. First, we will begin with the broader energy context, why underground and used resources are becoming important for carbon-neutral energy systems. Second, we will examine the current status of natural hydrogen research and commercialization around the world. Third, we will discuss the innovation strategy, especially the roadmap for stimulated hydrogen. Fourth, we will look at the key research challenges, including generation mechanisms, stimulation, recovery, monitoring, and risk. Finally, we will summarize the outlook and discuss what comes next for natural hydrogen as a future clean energy resource. Let us begin with the big picture. The global energy transition is not only about replacing fossil fuels with renewables. It is also about finding stable, scalable, and low-carbon energy systems that can support industry, transportation, and electricity demand. For countries with limited domestic energy resources, this challenge is even more important. That is why underground resources are receiving renewed attention. The subsurface is no longer just a place for fossil fuel extraction. It is becoming a key space for carbon storage, geothermal energy, underground hydrogen storage, and potentially natural hydrogen generation. To reach a carbon-neutral society, we must secure enough clean energy at large scale. Solar power and wind power are essential, and their costs continue to decrease. However, not every country has enough suitable land, offshore space, or grid flexibility to rely only on these options. Hard-to-abate sectors, such as steel, cement, chemicals, and heavy transport, also need clean fuels and high-temperature energy. This is why we need a broader strategy. In addition to solar, offshore wind, and clean energy imports, underground and used resources may become an important part of the carbon-neutral energy portfolio. Natural hydrogen is one of the most promising examples. Among underground and used resources, two options are especially attractive. The first is supercritical geothermal energy. Compared with conventional geothermal systems, supercritical geothermal could potentially provide much higher power output per site because of its very high temperature. The second is natural hydrogen. Natural hydrogen forms when water reacts with iron-rich rocks underground. One important reaction is serpentinization, where minerals such as olivine react with water and release hydrogen. The development concept has several levels. First, we could try to recover hydrogen that has already accumulated naturally. Second, we can inject water to enhance hydrogen generation. Third, in the long term, mined rocks or engineered systems may also be used to produce hydrogen. This means natural hydrogen is not only an exploration target. It is also a future engineering opportunity. Now let us look at where natural hydrogen stands today. For a long time, natural hydrogen was treated as a scientific curiosity. But in recent years, it has become a serious topic for clean energy, geoscience, and investment. Governments, universities, startups, and energy companies are now asking the same question. Can natural hydrogen become a low-cost, low-carbon, domestic energy resource? Why is natural hydrogen so exciting? There are four main reasons. First, cost. Natural hydrogen may be cheaper than imported green hydrogen or blue hydrogen because it may require fewer industrial conversion steps. Second, greenhouse gas reduction. If produced responsibly, natural hydrogen could have very low carbon intensity. Third, resource potential. Estimates of subsurface hydrogen vary widely, but even a small recoverable fraction could have major energy significance. Fourth, energy security. For energy importing countries, domestic natural hydrogen could reduce dependence on imported fuels. This is why natural hydrogen is now becoming a strategic research topic, not only a geological curiosity. Natural hydrogen forms through several subsurface processes. The first is radiolysis. Natural radioactive elements emit radiation that can split water molecules and produce hydrogen. This process is slow, but it can operate over geological time. The second is serpentinization. This is the most important process. Water reacts with iron-rich rocks, especially ultramafic rocks, and hydrogen is generated. The third possible source is deep or mantle-related hydrogen, where fluids may migrate upward through faults or plate boundaries. This idea remains under active scientific discussion, but generation is only part of the story. Hydrogen can also be lost through seepage, microbial consumption, or abiotic reactions. For production, hydrogen must either be trapped underground, recovered directly from fractured zones, or generated through stimulation. So natural hydrogen is a complete subsurface system: generation, migration, loss, trapping, and recovery. This slide shows the full subsurface hydrogen system. Water enters the subsurface and interacts with reactive rocks. In the deeper zone, hydrogen can be generated through radiolysis, serpentinization, or deeper geological processes. Then hydrogen migrates upward. During migration, some hydrogen may be lost. It can escape through faults and fractures. It can be consumed by microbes, or it can react with minerals and gases. The hydrogen that remains may accumulate beneath caprock, similar to conventional gas reservoirs. This is the target for production. The key challenge is to understand the balance between generation, loss, and accumulation. If generation is high, but loss is also high, the resource may not be producible. If generation, trapping, and preservation are favorable, natural hydrogen could become a real energy resource. Let us focus on serpentinization, the core hydrogen generation reaction. In this process, olivine-rich rock reacts with water. Iron in the rock is oxidized from ferrous iron to ferric iron. At the same time, water is reduced and hydrogen gas is produced. The rock is transformed into minerals such as serpentine, brucite, and magnetite. This reaction depends strongly on temperature, pressure, pH, mineral composition, fluid chemistry, and available reactive surface area. That is why laboratory experiments are so important. They help us understand which minerals generate hydrogen most efficiently, which temperature range is optimal, and how fluid chemistry controls the reaction rate. For natural hydrogen, chemistry controls the resource. There are two main pathways for natural hydrogen development. The first is stored hydrogen. This means finding hydrogen that is already accumulated naturally underground, then producing it like a gas resource. Stored hydrogen is attractive because the hydrogen already exists, but it is highly dependent on geological conditions. You need source rock, migration pathway, reservoir, seal, and trap. The second pathway is stimulated hydrogen. This means artificially enhancing hydrogen generation by injecting water or other fluids into reactive rocks. Stimulated hydrogen is more complex, but it may have fewer geographic constraints. Instead of only searching for places where hydrogen has accumulated naturally, we try to create favorable conditions for hydrogen generation. This is why stimulated hydrogen may become the more scalable long-term option. For geologically complex countries such as Japan, stimulated hydrogen may be especially important. Stored hydrogen can be very cheap if a productive reservoir is found. But stored hydrogen is limited by where nature has already created and preserved an accumulation. Stimulated hydrogen offers a different logic. If suitable hydrogen-generating rocks exist, we may be able to enhance the reaction and produce hydrogen more continuously. This reduces geographic constraints and creates a stronger connection between geology and engineering. For Japan, this is strategically important because domestic clean energy resources are limited, while energy demand remains high. Therefore, Natural hydrogen should not only be treated as an exploration target, it should be developed as a new subsurface engineering system. Stored hydrogen projects are already moving forward worldwide. Examples include projects in Mali, Kansas in the United States, Australia, Spain, and France. Many of these projects are currently in exploration or development stages, with production expected in the late 2020s or around 2030. This shows that natural hydrogen is no longer only a research concept. Companies are now drilling, testing, and building development strategies. However, this timeline is still uncertain. The key question is whether these projects can demonstrate reliable hydrogen flow rates, long-term production, economic viability, and environmental safety. The next few years will be very important for the natural hydrogen industry. Stimulated hydrogen is also advancing, although it is still less mature than stored hydrogen. Several companies and research groups are testing different stimulation concepts. Some focus on electrical fracturing. Some focus on chemical stimulation. Some explore microbial processes. Others investigate how heat, water, CO2, or catalytic reactions may enhance hydrogen generation. This is a very important point. Stimulated hydrogen is not one single technology. It is a family of technologies. The winning approach may depend on geology, mineralogy, temperature, permeability, depth, and cost. That means the field needs both fundamental science and field demonstration. One reason natural hydrogen receives so much attention is its potential cost and emissions advantage. Independent estimates suggest that natural hydrogen could be produced at a lower cost than many green or blue hydrogen pathways. Its greenhouse gas emissions may also be low, especially compared with conventional gray hydrogen. However, we must be careful. These numbers depend strongly on assumptions: drilling cost, flow rate, stimulation method, compression, purification, leakage, monitoring, and project lifetime. So the message is not that natural hydrogen is already guaranteed to be cheap. The message is that natural hydrogen has the potential to be both low cost and low carbon. But this must be confirmed through field data, life cycle assessment, and techno-economic analysis. Now we move from science to strategy. If natural hydrogen is promising, how do we develop it? The answer is not simple. Natural hydrogen requires a full innovation chain: exploration, drilling, stimulation, recovery, monitoring, safety assessment, regulation, and market creation. This section focuses especially on stimulated hydrogen because it may offer the largest long-term opportunity. At first glance, stimulated hydrogen sounds simple. Drill a well, inject water or another fluid, generate hydrogen, recover hydrogen. But in practice, every step is challenging. Exploration must identify reactive rocks and favorable structures. Drilling must reach complex, sometimes deep and fractured formations. Fracturing must increase reactive surface area without creating uncontrolled leakage pathways. Stimulation must control reaction conditions. Recovery must separate and produce hydrogen efficiently. And long-term operation must manage risk, monitoring, and maintenance. So stimulated hydrogen is not only a geochemical idea. It is a complete subsurface engineering system. Japan is beginning to build a national research portfolio for natural hydrogen. The selected projects cover several important directions. Some focus on ultramafic rocks and hydrogen generation enhancement. Some focus on national resource potential and artificial stimulation. Others study the factors that control hydrogen generation and stimulated recovery. There are also projects on hydrogen-generating rock exploration and regional resource development. This portfolio is important because natural hydrogen requires collaboration between universities, research institutes, and industry. No single discipline can solve this alone. We need geology, geochemistry, microbiology, drilling engineering, reservoir simulation, environmental engineering, and energy economics. This slide summarizes the major challenges. First, we need to identify where suitable sites exist and how large the potential is. Second, we need exploration, monitoring, and modeling methods. Third, we must understand reactive surface area. Hydrogen generation occurs at the contact between water and rock, so surface area is fundamental. Fourth, we need to optimize hydrogen generation conditions: minerals, temperature, pH, pressure, and fluid chemistry. Fifth, microbes must be understood because they may consume hydrogen or influence the reaction environment. Sixth, we need efficient hydrogen recovery technologies. Seventh, we need long-term operation and risk management. Eighth, we need techno-economic and life cycle assessment. And ninth, we should explore derivative technologies such as CO2 mineralization, rare metal recovery, and even natural ammonia. These challenges define the future research agenda. This slide maps the technology readiness level across the natural hydrogen value chain. Some parts of the system can reuse existing technologies from oil and gas, geothermal energy, and hydrogen infrastructure, but the upstream part remains immature. Exploration, drilling, fracturing, stimulation, recovery, and environmental risk management still require major innovation. This is where research investment should focus. The downstream hydrogen market already exists to some extent. The bottleneck is how to generate and recover natural hydrogen safely, predictably, and economically. In other words, to create the market, we must first solve the upstream technology gap. Technology alone is not enough. Natural hydrogen also needs a complete ecosystem. First, we need a national potential map. Without knowing where resources may exist, companies cannot estimate market size or investment risk. Second, we need whole chain demonstration. Upstream developers, midstream infrastructure, and off-takers must work together. Third, we need clear regulation. Natural hydrogen may not fit neatly into existing mining, gas, or geothermal laws. A clear legal status is essential. Fourth, we need social acceptance. Local communities may worry about drilling, induced seismicity, groundwater contamination, gas leakage, or environmental impacts. These concerns must be addressed through transparent monitoring, safety assessment, and communication. Natural hydrogen must be developed not only technically, but responsibly. The roadmap can be divided into several phases. From now to around 2030, the priority is basic research, technology development, and national resource survey. From 2030 to 2035, the focus shifts to commercialization studies, exploration wells, and field validation. From 2035 to 2040, pilot plant trials become essential. After 2040, commercial operation may become possible if the technology, economics, regulation, and public acceptance are ready. This roadmap is realistic because subsurface energy systems take time. We need laboratory data, simulation, field tests, monitoring, and business models. Natural hydrogen has great potential, but it must be developed step by step. This slide shows the technology roadmap in more detail. Potential assessment must begin with survey methods and resource estimation. Site selection must move from screening to test site selection and exploration wells. Fracturing technology must be developed to increase reactive surface area. Hydrogen stimulation must identify optimal physical, chemical, and biological conditions. Hydrogen recovery must become more efficient. Modeling must integrate geochemistry, flow, geomechanics, economics, and life cycle assessment. Monitoring must detect hydrogen generation, migration, leakage, and environmental impacts. And maintenance and risk management must support long-term operation. The final goal is clear. By around 2030, build the base technologies. By around 2035, validate the end-to-end system. By around 2040, move toward pilot and commercial operation. Now let us focus more deeply on the research frontier. Natural hydrogen is exciting because it sits at the intersection of many fields. It is chemistry because reactions generate hydrogen. It is geology because the resource depends on rock type and structure. It is reservoir engineering because hydrogen must migrate, accumulate, and be recovered. It is geomechanics because stimulation changes stress and fractures. It is environmental engineering because leakage and impacts must be controlled. And increasingly, it is also artificial intelligence because the system is complex, uncertain, and data-intensive. The ARPA-E Geologic Hydrogen Program in the United States provides an important example of research direction. A large share of topics focuses on hydrogen generation enhancement and reaction condition studies. This tells us something important. The field is not only asking, where is hydrogen already stored? It is increasingly asking, can we generate hydrogen in the subsurface? This is a major shift. The emphasis is moving from passive exploration to active engineering. Operations and safety are also important, even if they represent a smaller portion of the research portfolio. For commercialization, enhancement, operation, and safety must all be solved together. The ARPA-E projects cover several technology directions. For fracturing, researchers are studying cyclic hydraulic fracturing, electrical fracturing, CO2 gas fracturing, and conventional hydraulic approaches. For stimulation, projects examine chemical stimulation, catalytic effects, and microbial effects. For recovery, researchers are also exploring advanced methods such as foam-assisted hydrogen recovery. This diversity is important. It shows that natural hydrogen is still in a discovery phase. The best technology pathway has not yet been selected. Different geological settings may require different solutions. That is why comparative experiments, field pilots, and integrated modeling are essential. Natural hydrogen may also open the door to other subsurface chemical technologies. One example is natural ammonia generation. Researchers have explored the idea of injecting nitrate-bearing water into iron-rich rock. Under suitable conditions, reactions involving iron-bearing minerals may produce ammonia. This is still early-stage research, but the concept is powerful. It suggests that the subsurface could become more than a storage space or extraction zone. It could become an engineered chemical reactor. In the future, subsurface reactions may support hydrogen production, ammonia production, CO2 mineralization, critical mineral recovery, and other clean energy processes. This is an exciting frontier for geoenergy research. Let us summarize the main message. Natural hydrogen is emerging as a promising clean energy resource. It can be generated underground through reactions such as serpentinization. There are two main development pathways: stored hydrogen and stimulated hydrogen. Stored hydrogen focuses on finding existing accumulations. Stimulated hydrogen focuses on enhancing underground reactions to generate hydrogen. Globally, research and commercialization activities are increasing. Japan has also begun building a national research portfolio involving universities, research institutes, and companies. However, practical deployment still requires progress in exploration, drilling, stimulation, recovery, monitoring, risk assessment, regulation, and social acceptance. The key message is this: natural hydrogen is not only a new resource, it is a new subsurface energy system. Thank you very much for watching. Natural hydrogen may become one of the most exciting clean energy frontiers of the 21st century. The Earth may already be producing hydrogen beneath our feet. The challenge now is to understand it, locate it, stimulate it, recover it, and manage it safely. For researchers in geoscience, environmental engineering, reservoir simulation, geochemistry, and artificial intelligence, this is a major opportunity. If you found this video useful, please like, subscribe, and share it with colleagues interested in clean energy, CCUS, underground hydrogen storage, geothermal energy, and subsurface engineering. And please leave a comment. Do you think natural hydrogen can become a real clean energy industry? Or will it remain mainly a scientific curiosity? See you in the next video.